Have you ever just stopped and wondered, how does a computer actually understand the code we write? I mean, it's so easy for us to just hit compile and take the whole thing for granted, right? But how does a machine look at a screen full of human text and turn it into working apps? Well, it's definitely not magic. It's actually thanks to some truly fascinating mathematical models. Welcome to this explainer. Today we're climbing the ladder of abstraction to decode the hidden architecture of computation. We're going to be looking at the applications of automata, these brilliant underlying models that make everything from compiling code to natural language processing actually possible.
Okay, let's dive into this. Here is our roadmap for today. We're going to hit 5 key stages. First, the basics of string recognition. Then, defining syntax and language. From there, parsing and evaluating expressions, the limits of computation, and finally, real-world impact and outcomes. We are literally climbing from simple pattern matching right up to the absolute peak of computer science.
So, to really picture how these models work, I want you to imagine a highly efficient factory. Let's go ahead and call it the compiler factory. When you write code, it has to move down this assembly line to become executable software. It's broken down into 3 main phases. Phase 1 is lexical analysis, where your raw text is chopped up into meaningful chunks. Then comes Phase 2, syntax analysis, checking if those chunks actually follow the rules. And finally, Phase 3, parsing, where the real structure is built. Automata? Well, they're the dedicated factory workers at each station moving your code seamlessly down the line.
All right, let's start right down on the ground floor of our factory. Section 1, the basics of string recognition. Meet our very first type of worker, the finite automata, or FA. By definition, an FA is a model used for recognizing what we call regular languages and searching for specific patterns within strings. You can really think of them as the initial pattern spotters in our compiler factory. During that first phase, lexical analysis, their one and only job is just scanning through thousands of characters of your code and grouping them into recognized keywords, variables, or symbols. They're fast, they're efficient, and they're absolutely fundamental for making sure your code's raw vocabulary actually exists. But here's the kicker. What makes finite automata so incredibly powerful is that they do way more than just read code. Sure, they handle lexical analysis and compiler design, but they also moonlight as security guards. In network security, FAs are heavily used in intrusion detection systems. So instead of looking for, say, a while loop, the FA is out there scanning network traffic for specific, malicious string patterns that might signal a cyber attack. It is literally the exact same mathematical model reading your code and protecting your servers. Pretty cool, right? But hey, recognizing words is just the beginning. We need to understand sentences. Let's move to and see how this builds in Section 2, defining syntax and language. So once those finite automata have picked out the basic words, context-free grammars, or CFGs, take the wheel. These are essentially the rulebook writers of our factory. CFGs define the overall syntax of programming languages, making sure that, for instance, a return statement actually sits inside a function where it belongs. They're super crucial for parsing source code. But what's wild is that their application doesn't stop at computer languages. We also use them to model the syntax of human languages in natural language processing. They literally help computers parse and understand the sentences you and I are speaking every single day. And expanding on that, our source explicitly calls out CFGs as the foundation of computational linguistics and natural language understanding. This isn't just dry theory. This has massive real-world societal relevance. I mean, think about voice assistants, automated translation tools, accessibility software, all of it. Designing these CFGs directly impacts how we humans interact with machines. The source highlights this as a major learning outcome. You've got to understand the societal relevance and realize how important it is to stay updated in such a rapidly moving field.
Now, rules are great and all, but what happens when those rules get a bit complicated? Let's transition to Section 3, parsing and evaluating expressions.
Consider this for a second. How do computers evaluate complex arithmetic and actually enforce nested rules? Simple pattern spotting just isn't going to cut it anymore. If I open a parentheses in a math equation, the computer has to somehow remember that I opened it so it can make sure I close it later. The thing is, finite automata actually don't have the memory for this. We need a serious upgrade.
Now, what's really interesting about this slide is how it tackles balanced parentheses checking. To check if a sequence of brackets is perfectly balanced, we bring in the push-down automata, or PDA. A PDA is basically a finite automata with an added superpower, a memory stack. When it sees an opening bracket, it pushes it onto the stack. When it spots a closing bracket, it pops the matching one right off. If the stack is totally empty at the end, boom, the structure is perfectly balanced. This is exactly how your code editor instantly yells at you when you forget to close a curly brace.
The roles of the pushdown automata are actually huge. They're the engines that parse those context-free grammars we just talked about. They evaluate complex arithmetic by keeping track of operations in that memory stack. And remarkably, as another self-learning topic from our source notes, PDAs are absolutely essential for designing programming language interpreters like the ones used for Python and Java. Honestly, without the memory stack of a PDA, the syntax analysis phase of modern compilers simply would not work. No way around it.
All right, we are officially approaching the very top of our abstraction ladder. Section 4, the limits of computation.
We've finally arrived at the heavyweight champion, the Turing machine. As our source material highlights, this model is famous for simulating any algorithmic process, providing a theoretical foundation for computational studies. See, Turing machines don't just compile code, they help us understand the fundamental limits of computation itself. We use them to analyze the efficiency of algorithms. Put simply, if a Turing machine cannot compute a problem, no computer that exists or ever will exist can compute it. It's the absolute ultimate benchmark of what's computationally possible.
So we've got all this incredible theory, spanning from basic pattern matchers to the absolute limits of computation. But what does all this actually mean for you? Let's look at our fifth and final section, real-world impact and outcomes.
And this brilliantly illustrates how this deep dive into mathematical models maps directly to your development as a professional. Look at this. Understanding finite automata isn't just about compilers. It actually trains you to analyze project feasibility. Mastering context-free grammars connects you to the societal relevance of software, which is huge as AI reshapes our world. Working with pushdown automata is directly tied to collaborating in teams and writing well-structured technical documentation. And finally, exploring Turing machines, that instills a profound recognition that you have to keep learning in a field that literally never stops evolving.
Bringing it all together, the outcomes for the modern developer are super clear and entirely actionable. By grasping these concepts, you aren't just learning how to design automata-based models. You're learning how to evaluate their broader impact on modern software. You're learning to analyze information for feasibility and, crucially, implement sustainable computing practices. You become an engineer who can produce clear, well-structured technical reports and collaborate effectively to solve incredibly complex problems. Basically, you go from being just a code writer to a true architect of computation.
Well, we've scaled the ladder, from basic string recognition all the way to the theoretical boundaries of what machines can actually do. These models, finite automata, context-free grammars, pushdown automata, and Turing machines, they are the silent gears turning inside every single digital device on Earth. So, knowing the limits of computation and understanding the elegant rules that govern it all, what part of the compiler factory will you build next? Think about it and keep exploring.